Okay, guys, lesson 8. You've already discovered. Looks like a bunch of pre-cal review, and it is. Okay, so Pythagorean identities. There's 3 of them. They still come into play, right? Probably the most common one is the sine squared theta plus cosine squared theta equals 1. The other 2 are the ones that I always have to think a little bit harder about, but the tangent squared theta plus 1 equals secant squared, and cotangent squared plus 1 equals cosecant squared. And the one thing is, keep in mind that as we talk about this, these are true for any theta. So for any value of theta, these statements are true. Okay? So be familiar with those. Example 1 here, sine squared of 17 degrees plus cosine squared of 17 degrees is equal to 1, right? I know the tendency is, I want to get the calculator out and do that, but if you can catch it, it's that Pythagorean identity. Sine squared of an angle plus cosine squared of the same angle is always going to equal 1. If only they were all that easy, right? Or all went that quickly.
It's like the baby calc test is one thing.
If only. Okay. Topic B, functions of negative theta. So this is okay. We had these special negative identities, and what happens when the variable is negative, right? When it's a negative x or negative theta. So sine of negative x, cosine of negative x, and tangent of negative x. And what you have to remember is that does not just mean that the function is negative. Okay? If it's sine or tangent, then sine of negative x and tangent of negative x, yes, they are equivalent to the negative versions of the functions. Cosine, however, cosine of negative x is cosine. Okay, there is no negative. And this comes back to, I don't know how much you guys remember about even and odd functions. Okay, these 2 right here, the sine and the tangent, are odd functions. Okay, whereas cosine is an even function. Do you remember anything about odd and even? Okay, well, one way, there's 2 different ways to tell, as we look at functions, to tell if something is even or odd. One is by looking at the graph, and one is by looking at what happens when you put a negative in and stuff. Okay, so an even function, you can tell something is even if it is symmetric across the y-axis. Okay, that is an even function if they are symmetric across the y-axis. Okay, so, and you guys know what that means, right? Draw that vertical line, you can fold it in half, symmetric across the y-axis. Now, odd is also symmetric, but it's not the x-axis. It's symmetric across the origin. If a function is odd, it's symmetric across the origin.
I think we did stuff with this last year.
And we did stuff with it. It's just a matter of what you remember. But when I say symmetric across the origin, it has like a diagonal type symmetry, kind of. I almost think of it as you reflect it across both axes. The x, if you take a quadrant, you flip it across the x-axis and then flip it across the y-axis, that's symmetric across the origin. So, and we can look at some graphs as we go, but the other option is using f of negative x and negative f of x and seeing how they equal. So let's see, and I'll put it down here. So down here it talks about cosine and secant are even functions, right? And I already talked about cosine is an even function. Of course, secant is the reciprocal of it, so it goes right along with it. But the other way to tell if something is even if the original function f of x is equal to f of negative x. So if you just put a negative x in place of the variable x, and it works out to be equivalent, that's another way of knowing that a function is even. If a function is odd, and so right here, sine, we already talked about sine being odd, and thus cosecant is odd. If it's odd, do you remember this one? F of negative x. So when you plug the negative, it's not equal to the original, but it's equal to the negative of the original. So multiplying the whole equation by a negative. Okay. And then tangent, since tangent and cotangent are a combination of sine and cosine, then they are odd functions. Okay, so be familiar. I don't know, comes up in various ways, shapes, and forms. Okay, let's do some simplifying. Sine of negative theta times cosine of negative theta, all divided by tangent of negative theta. Well, what do you know about sine of negative theta? Okay. It is the negative of sine theta. Cosine of negative theta. What do you know about cosine of negative theta? It's just cosine theta. And I'm just using my even-odd identities, right? That's what they were called, even-odd identities. Tangent of negative theta? Negative tangent theta. Okay. I would like to think, obviously, you know you can't stop here. You go as far as you can go. Thoughts? I would change tangent to sine over cosine. Now, and keep in mind, it's dividing by tangent. So it's dividing by sine over cosine, which is then going to be multiplied by the reciprocal. So I'm going to write this out as negative sine theta, which negative sine theta as a fraction is negative sine over 1, if you will, times cosine theta. Cosine theta as a fraction is cosine over 1 times, well, it's divide by negative tangent. So it's divide by negative sine over cosine, which means it's going to multiply by negative sine over cosine? No. Yeah. I said it one way in my head and then okay, don't do what I did. I'm not even sure what I did there. So it's divide by sine over cosine. So then we're going to multiply by cosine over sine. I honestly think throwing the negative threw me off. Bad excuse, but that's like what got my brain off. Okay. What kind of cleanup you going to do now? Mm-hmm. So the sine cancels with the sine. And then we have a negative here and another negative here, which is going to mean negative times negative is going to make it a positive. Okay. What's this going to clean up to be as a final answer then? Yep. Cosine squared theta. See, and you guys thought that stuff was horrible last year.
Well, I mean, I'm not going to start talking trash to it until after the first test. So far, so good.
I feel like there was one of these in the last one.
It was like...
They could have been prepping you for it.
It said compute cotangent of 7 over 3. I remember that one. And it said review. I'm like, what?
Technically, it's a review. Whether you remember how to do it or not, it's a whole different story. But, yep. Okay, example 3. Tangent of negative theta times cosine of negative theta minus sine of negative theta equals 0. Show that for all values of theta, that makes sense. So it's kind of like prove it, right? Which basically just means work with it until both sides are the same. Which means it says equals 0. Just keep the equal 0 on the right. Our goal is that the left will eventually equal 0 as well. Okay, that's, when they say show, in my mind, that's another word of saying prove. Okay, so based on things we've talked about, things we've done, what do you know about tangent of negative theta? Okay, it's odd, so it's negative tangent theta. Cosine of negative theta? Just cosine theta. Minus sine of negative theta? Negative sine of theta. And I'm just going to write equals 0. I'm just going to keep it the same and hope it works out. I mean, that's my goal, right? Or I guess I could write the equal 0 at the end. Okay, next thoughts? Okay, tangent is sine over cosine. So we can rewrite this as negative sine theta over cosine theta times cosine theta, which cosine theta is a fraction, cosine over 1. And if I keep writing it out, minus a negative sine theta is really just going to be less sine theta. And then equals 0 still. And what do we know? Cosines cancel. Negative sine theta plus sine theta. And does that work? Are we at a point we can stop now? Yeah, negative sine theta plus sine theta, that equals 0. You're there. If you want to go that one more step, you can say 0 equals 0. Okay, however you want to do it, but that definitely checks. I don't know. There was a point last year that you guys would have been like, what did you just do? I don't know. Maybe that was more of your counterparts. Maybe it wasn't as much of you guys. Or maybe it just all makes that much more sense now. So, okay, down there at the bottom, it talks about steps to take to solve identities. And kind of some of what we're just doing right now in a way, but it's not so much steps as is in recommended things to consider, okay? Substitute an equivalent expression for all or any part of a given expression. Okay, that could be things like thinking about your Pythagorean identities and substituting those in. Okay, looking for equivalent identities. Multiply numerator and denominator of any expression or a part of an expression by the same quantity. Maybe trying to convert so they have common denominators or convert, so, just looking for ways to put them together. And combine terms that have like denominators. So, again, steps, I don't know, things to think about, recommendations. Let's try them. Show that the following relation is true for all real numbers x where the functions are defined. So basically, again, we are talking prove it. So cosine squared x plus 4 plus sine squared x all over 5 secant squared of negative x is supposedly equal to cosine squared x. Any thoughts of where you want to begin? And what do we know about cosine squared x plus sine squared x? Those two combined together via our Pythagorean identity will be 1. So what's that make my numerator? 5, right? Yeah, eventually. As in, I'm not quite ready to do that yet, but okay. So we're convinced the top becomes 5. The bottom, we have 5 secant squared of negative x. for secant of negative x?
It would just be something.
Right, because secant is the reciprocal of cosine, so it's going to go with cosine. So secant of negative x is just going to be secant x, right? So then secant of negative x quantity squared is really just secant x squared. And there's a 5 out front. So I have 5 over 5 secant squared x. Okay, now I'm willing to cancel the 5s. I cancel the 5s, I now have 1 over secant squared x. What do you know about 1 over secant squared x? It's the reciprocal of cosine, which means it is cosine squared x. And that's what I was looking for, wasn't it? I was looking for cosine squared x. Hopefully you're seeing these a little bit with me. I know last year it was really rocky. I'm hoping it's less rocky this year. Okay, one more. Show that cosine squared x, secant squared x, minus cosine squared x equals sine squared x for all real numbers x where the functions are defined. Starting thoughts? Yeah, officially they'll cancel each other out. The way I would show it is that cosine squared x as a fraction is cosine squared x over 1. What do you know about secant squared? It's reciprocal of cosine, so it's 1 over cosine squared x. Okay, and then I'm going to write it, it's still minus cosine squared x after that. But yeah, so cosine and secant are reciprocals. So when you multiply reciprocals, they cancel and you're just left with 1 minus cosine squared x. Which would what? And why is that? Yeah, I'll jot it down over here. Pythagorean identity, sine squared x plus cosine squared x equals 1, doesn't it? And so if you take the 1, you subtract the cosine squared over 1 minus cosine squared x just does so happen to be sine squared x, which was our goal. And that's where it's handy, I kind of taught last year. When you see any trig functions being added or subtracted together and or ones thrown into the adding and subtracting together, it's very possible to think Pythagorean identities, isn't it? Not going to guarantee it works, but it's definitely worth a consideration. Okay. Okay. That really all focused on practicing those even-odd identities. We also had some cofunction identities. Okay. The following are considered cofunctions of each other. And it really just comes to do with their phase off of each other. They are 90 degrees off of each other, or what's 90 degrees? In other words, pi over 2. Okay? They are a pi over 2, a phase shift off of each other. So basically, cosine and sine, they're cofunctions, right? They're the same graph, just shifted over. Tangent and cotangent, secant and cosecant. Okay? It's always pi over 2 minus theta, or 90 degrees minus theta. But just realize, cosine of pi over 2 minus theta is equal to sine. Flip it around, sine is equal to cosine. Okay, so know the pairs is what it comes down to. Okay. Now, with those in mind, we've got another show. Show, prove, however you want to consider this, that sine squared of negative theta times cosecant squared of theta minus 1 times cotangent of pi over 2 minus theta is equal to sine theta cosine theta. I honestly like these better just because they're more obvious what to do. I mean, the even odd identities. When I see a negative on the variable, I know I have to get rid of that negative. So what do you know about sine of negative theta?
It's negative sign.
It's negative sine. And it's negative sine theta, but what am I doing with this? I'm going to square it. What is negative sine theta when I square it? Sine squared theta. So realize you take that negative out front because it was odd, but negative times negative is going to make it positive, so it just makes it positive sine squared theta. Okay. What about cosecant squared theta minus 1? Okay. According to our Pythagorean identities, cotangent squared theta plus 1 is equal to cosecant squared theta. So if you have cosecant squared theta and you subtract 1, it is going to be equal to cotangent squared theta. What about cotangent of pi over 2 minus theta?
So that would be
Tangent theta. Okay. Next.
get them all the sines and cosines.
Yeah, turn them into sines and cosines. Sine squared theta, I am going to put it as over 1, but other than that, abstain. Cotangent squared theta,
Would be cosine squared theta over sine.
cosine squared theta over sine squared theta, and tangent theta. Sine theta over cosine theta. Okay. Anything happen here?
The sine squareds cancel. One of the cosine squares cancels with the cosine squared below.
Okay.
So you end up with cosine theta times sine theta.
Okay. Sine squared cancels with sine squared. One single cosine theta on bottom cancels with one of the cosine thetas on top, leaving us with a cosine theta and a sine theta on top. And cosine times sine, well, I wrote it as I was looking at it, cosine times sine, which we're going for sine times cosine. Good enough. Okay. If you've made it this far, you know that's equivalent. Okay. Similar triangles. I feel like this is a pre-calculus review. Okay. We might have worked with similar triangles at some point during pre-calculus. Not going to say we didn't, but similar triangles, more of a geometry topic. So, when you have similar triangles, you can solve using proportions. Now, the key is being able to identify some of these similar triangles. And if there's several varieties here, some of them are more obvious or easier, some of them are a little more difficult, which is why I do want to take the time to talk about them. You guys know how to do the easy version of these. The question is, can you do the difficult version of these? Okay? So, none of them are quite as easy, obvious, but okay. This is something you would have seen way back when, right? Do you see your similar triangles? There's a small triangle here, yes? I'm going to go ahead and draw that small triangle off to the side here. In that small triangle, I know there's sides of 6, 4, and a hypotenuse of x. And then there's also a big triangle, yes? And again, it's not that you have to redraw these triangles. It just makes it easier for me to point and talk about them. What are the sides in the big triangle? Okay. x plus b, c, and 10. And that right there, having that x plus b and stuff, this is where life gets a little more confusing. Our directions were to find b. Now, this is always interesting. How do you guys set up your proportions?
So, you want to just say how it should have the proportions?
Yeah, like what? There's different various proportions we could write here that would work.
So I would do 4 over 6, 1 over C over 10. So they can like that, right?
Okay, so if 4 over 6 is equal to c over 10. Now, here's my question. Do I have to know c?
No, but the way I was going to do it was I was going to find C. You can do the Pythagorean theorem to find X. And I was going to find C, the Pythagorean theorem with that, and find B that way. But that would how it would be looked up.
Interesting.
I see what you're doing.
I see it. I see it. I'm not going to argue it. Not at all the direction I was going. Okay. I was going to go more of the direction of go ahead and set up my proportion that involves the B. I was going to go straight to that one. Not saying that wouldn't work though. I feel like, it should. Barring, the only issue you could run into is if you round too much or something, it throws your answer slightly off. But it should work. And what are we going to have to, C, here's my thing. I can do this problem and never worry about C. You could find C and it could work for you as well. Okay. But what are we going to have to know at some point? In order to find B, we're going to have to know X. Can I find X? Yeah. I would jump right in and let's find the Pythagorean theorem on that first triangle. And so I'm going to write it, I'm going to go off to the left here. And Pythagorean theorem says 4 squared plus 6 squared equals x squared. 16 plus 36 equals x squared. 16 plus 36 is 52. And so if x squared is 52, then x is square root of 52. What does x simplify to be? Not decimal. I'm not going to go decimal here. What's the perfect square in 52? 4 times 13? So it'd be 2 square root of 13. Okay, so what I know over here is that every place there's an x, that x is really 2 square root of 13. Of course, it can work out to be a nice, neat number, couldn't it? That would make life way too easy. Now, you guys don't need to see my Pythagorean theorem work, do you? Okay. So, based on that, I was going to set up a proportion using the side that involves B. Okay. And I guess when I was asking it earlier, it's kind of, I'm trying to remember which way Ross said his when he did it. Some people do like small triangle to big triangle, small triangle to big triangle. Other people do like hypotenuse to long leg, and then in this triangle, and then in this triangle. And I don't know which way you guys do this. Does that make sense? I guess what I'm saying is there's multiple different ways we could set this up.
Yeah, I mean, the way I would want to do it in my head, at least, would be I would do the small one first, and then the second one second.
So you're going to say 2 square root of 13 over 6 or vice versa.
Yeah.
And then is equal to this triangle. Is that what you guys do?
That's what I would do.
Okay. And that's fine. It works. I tend to go.
McNally, please report to the nurse's office. Dakota McNally.
I would tend to go more like 6 like 6 over 10 and 2 square root of 13 over 2 square root of 13 plus b. And I don't know, maybe that's just the way it's ingrained in my head from years ago, but so no, I'm fine either way. So if we're going to say that, 2 square root of 13 over 6. So the hypotenuse from the small over the long leg from the small, right? Equals, now be consistent, right? If we did a hypotenuse on top, we're doing it again. So 2 square root of 13 plus b over 10. Are you guys okay with that? How do we solve a proportion like this? Cross multiply, right? Cross products. And here's my deal. If you want to do a different setup, your cross products need to match my cross products. And if your cross products match my cross products, then you have a valid setup. Okay? So, cross products, fun stuff here. You guys got cross products down, right? 6 times 2 square root of 13 plus b is going to equal 10 times 2 square root of 13. Okay. We're going to distribute. 6 times 2 square root of 13 is 12 square root of 13 plus 6b equals 20 square root of 13. In order to get the 6b by itself, I'm going to subtract 12 square root of 13. So 6b is equal to 20 square root of 13 minus 12 square root of 13. Eight square root of 13. I assume that was okay. And how do I finish solving? Divide by 6. And when you divide by 6, what is 8 square root of 13 divided by 6?
8 squared.
There's one.
4 squared of 13.
Yeah, there's one small simplification step we can do. Think about 8/6 is just a regular fraction. 8/6 can reduce to 4/3. So yes, I agree. 4 square root of 13 over 3. The more difficult level of similar triangles, right? You know the basics, but it's going past the basics here. Okay, questions on that one? You got it? Okay, we do have, it's another day where we have a third page. I assume you see the two triangles here, right? Should be a little more obvious. We've got my small triangle right here. And we have our big triangle. I don't think on this one I'm going to draw the two triangles separately. I think we can see them here, okay. What is the proportion? I mean, you don't know the hypotenuses, so we don't have to worry about that. What is the proportion you would like to set up?
I did x and h, and then so x over h is equal to p over b plus p.
X over h. So he did left side to left side. And then what'd you say?
Is equal to p over d plus p.
P over d plus p. I can handle that. Okay. If you, instead of doing x over h, what if you did x over p? If anyone did x over p, then you'd be doing h over d plus p. Here's the deal. Do your cross products match my cross products? That's what matters, right? What are we solving for? Yeah, we have to take this mess and solve it for p. So let's go ahead and cross product. Can you handle it if I go ahead and distribute? Yes.
I think I might be missing something. So I thought it would be like, because it would be x divided by h, it would then be p divided by d plus p. Or did I just write the wrong thing?
That's what I have written down, isn't it?
Okay, I think I just wrote
Had my screen already gone off when you started asking that?
it. Might have been mixed up with these and these.
I feel like what you said is what I have
What
written.
you said is correct,
Okay, I just had.
but it was also what you had.
Which is why I was struggling with, well, wait a minute, where's the deadline? Okay. Sorry, I just ran over. So are we good with this setup then? Okay. So if I do cross products, H times P,
Easy.
HP, or PH, whatever makes you happy, X times D plus P, plus XP. My goal is to solve for P, so put the P's on the same side.
Yes, that's right. Yes.
So I'm going to have HP minus XP equals XD. And here's the step that you need to, do you remember how to do this next step?
Factor it out.
Yep.
And then that's in.
Yep. Yeah, since P is in, we can't subtract those terms, but P is in both. So we're going to factor it out as a GCF. So then I'll have a P, and then I have H minus X equals XD. And since it's P times H minus X, we can divide by H minus X. So P equals XD over H minus X. Okay. Can I just write down the answer for number 9? I think number 9 is very similar to what we just did. It is. It's very similar to what we just did. I'm going to get to example 10. Excuse me. So I'm just going to tell you, unless you feel the need for me to work out 9, what my answer key says. I have the final answer as AX over B minus A. But I really want some time to spend on 10, because 10 is different. You guys are looking at like it is. Doesn't look that different. Okay, guys. What do you see in the way of triangles there? Do you see the triangles? Okay. I'm going to draw the triangles down below so I can reference them. We have the whole big triangle. Yes? And with that whole big triangle, what do we have? The right angle at the top, a Z on the longer leg, a Y on the shorter leg, and what is my hypotenuse? 12. That's the whole big triangle. Do you see that? What's the next obvious one? Little small guy here? Little small guy. Right angle is down at the bottom right. What do we know? Short leg 3, long leg X, hypotenuse Y. Do you see the third right triangle that we need here? There's a third right triangle, and it's the right part of the big triangle, isn't it? So it has the right angle in the bottom left, and it has short leg X, long leg 9, hypotenuse Z. And here's the deal, folks. You have to use a combination of all 3 of those. You can't just use 2 of them. My goal is to find X, Y, and Z. And never is there a way that I can just easily, find them all. We kind of have to mix and match. So, okay, pick a way you want to get started. I know how I did this. I know how I've done this. Okay. Like, I guess, here. What if I say, let's look at the short legs over the hypotenuse and see what we come up with. So if we look at short leg over hypotenuse, in my first big triangle, it was what? You and I are not looking at the same one. That's the next small triangle, but yes. Okay. No, you're fine. Okay.
I wrote them on my paper. I wrote them small.
That's fine. Okay, so I have y over 12 from one of the triangles, right? It's the really big one. If we're doing, there's also, if you do the short or the smallest triangle, it's 3 over y. And what about that, what I'd call the middle triangle? If we're doing short leg over hypotenuse, it is x over z. I didn't do very good about making my short legs the shorter legs. Now, here's the deal. We got 3 pieces. We really only need 2 pieces. Are there 2 of those pieces that work? Yeah. Basically, ignore the x over z, because that just adds chaos. If you just use the other 2 parts, you have just numbers and y's, don't you? So if we look at our cross products then, y squared is 36, and thus y is 6. Okay, so notice what we're doing here is we're doing ratios of 2 triangles at a time. Okay, so there I was doing the short leg over the hypotenuse. Now, pick another combination. I have in my notes written the short leg over the long legs. So if I do the short leg over the long leg, that triangle is y over z. Then I have 3 over x in my smallest triangle, and that middle triangle is x over 9. Is there a pair of those that work now? We can use the 3 over x and x over 9, can't we? X squared is 27. So x is the square root of 27, which can also be written as 3 square root of 3. And, you know, a method that I'm sure some of you are doing without me, or you say you prefer to do, once you know that y is 6, could you fill that in and use it places? You could. But my point is we don't have to fill those in. We can do them all. You just have to, you know, be careful. So now if I look at the long legs over the hypotenuses, the one combination I haven't looked at. Z over 12, X over Y, and 9 over Z. Well, this time, I'm going to ignore the X over Y, aren't I? And so then you're looking at Z over 12, 9 over Z. Z squared is it 108?
Yes.
Okay. So Z is square root of 108. That's the easy part. What is it? 6 square root of 3. 36, that's what it is. It's the beginning of school year. My brain wasn't, I was like, I know there's something in 108. I just haven't figured, I can't remember what it is. So, okay, so, you know, different techniques, you can look at that. I'm sure you guys can come up with some other variations, but the idea that I did is I did ratios of 2 triangles at a time. Now I kind of wrote out all 3 so you can kind of see them, but, you know, there are different variations you could do there. Yes?
So could you have done, like, instead of short over hypotenuse, could you have put those?
Yep.
Like, for all of them?
Yeah, you could have done hypotenuse over short. You would have had 12 over y, y over 3, z over x. And so you still would have been using these 2 and gotten the y squared equals 36. Yep. Yeah, I just randomly picked short over hypotenuse, but hypotenuse over short works too. As long as you flip them all, it works. Okay, that's my last of the notes, right? Didn't think I had anything on the next page, but okay. We've got a few minutes. I can at least glance at homework, and I want to hand out the review worksheet a little bit. That way, if you want to start looking at it, you can. Don't have to.